Hey, welcome back to the Halite series. In the last episode, we ended implementing the training script to a point where it could potentially be run, and we still had one issue with the NumPy library that couldn't load its stored values. It said something about allow pickle equals false. And I looked deeper into it, and I found that in, I think, the newer versions of NumPy, they actually added this flag. And you need to set it to true if inside of this stored NumPy array, you have any Python objects that NumPy needed to pickle. And we had this initially here. I tried to remove it, but our states, action indices, rewards, and dones arrays were actually Python arrays. Right, maybe I can just do a git diff. Let's just see. This is in your network bot, exactly here. So previously we stored it just the states, action indices, rewards, and dones, which are Python arrays. So storing it in this way would pickle all of these arrays. And then when you load it, you have to tell NumPy that you explicitly want to allow unpickling stuff, because this can be dangerous if you don't know what you're reading. I tried to overcome this by wrapping this in NumPy arrays to convert it, but it still didn't work. I have to look into this a little bit more, where I exactly still store some Python object, maybe in the states or something. Anyway, I fixed this and then it ran. I still had to do some changes where let me see. I committed it last episode, so we should see all the changes that I did. So I moved some stuff around. This one, did I really commit this? Maybe I didn't commit this. Okay, this was a mistake then. I should have committed so we would actually see the diff now. But I think I had to wrap this train X and train Y into NumPy arrays as well. The rest, I think, just... didn't work neither. So we loaded the training data like this. We appended all the NumPy arrays that we found. And now we had a single loop. Basically, this as the outermost loop. What happens though is that each of these load commands loads one full game containing 9 samples or something. So we need to iterate for every game in the training data. We want to predict all the states, and then we can iterate over the states and the already predicted Q values. So then we can actually iterate over the current state, the current queue, the next state's queue, the action indices, index, the reward, and the dones. And then we can basically run this update function. And then this actually worked as it is. I store the model. Yeah. A couple of other things I noticed. So I ran it because, of course, I was curious. And I found that, for example, this import TensorFlow STF takes a couple of seconds for me. So even in the case where we only make random moves, it would take, I don't know, 2 or 3 seconds per game. So I went ahead and Googled this. I couldn't find any immediate solution until I found a good solution. I actually, in our bot, said if our epsilon is 1.0, we only import, if it's not, we only import TensorFlow if it's not 1.0. And then I can run 5 games like per second. And let me show this. Is it still here in the history? So, okay, there's a lot of errors. I'm going to go over this too. We're going to fix this. Let's see. This one. Ugly. Okay, here. So we start the training, we have all these warning outputs, which is also something I want to check how I can make it go away. So one thing I have now, since I start casting these into NumPy arrays is that sometimes I get this error where it says it cannot cast this states array into the same shape as the others. So I have to check this, and maybe it's not so good to have different arrays of different shapes in the same NumPy array. When I read about it, it seemed that this NumPy tries to cast them all into the same shape so that it can determine what's the shape of the outermost array. You can see I actually ran this, so you can see I can make about 4 games per second if I don't import TensorFlow. I ran this for quite some time to get 1,200 games. The average reward on 1,200 games is minus 34. Let's just check real quick. So here you can see this. The first number is the rewards that we get. We have kind of a couple of rewards that are positive. Actually, one game we even had where it managed to get 571 reward, which is interesting because I thought the best possible moves was 400 something. So it would have been interesting to see the replay of this one. And then you can see it decreased the epsilon for 10 episodes or something. Yeah, here we collected these 9,800 samples, which is not so much actually, so we could probably run this for quite some more time. We trained for 5 episodes. It immediately has a pretty high accuracy, so it seems to be able to determine, at least as a class, to determine the correct move with the highest reward quite often. But yeah. Here's some more warnings which I should actually look through and read why I get them and how I can prevent this. Here you can see we still have an issue where if we actually try to create this folder inside a bot, it will tell me sometimes that the file exists because the other bot already created it. And this is something we should fix by probably creating this folder outside the bots. Then here's some TensorFlow warnings. There's this broadcast error again. I think the only thing that happens is that for this one particular game, it doesn't store any results. So you can see in Epoch 1, we have 138 files. Reward is also negative. It's minus 43, which is actually worse than the previous, but we still make like 80% random moves, so or 95% random moves, I guess. Our accuracy is quite high, but again, we have very few training data, and I wish we would collect more, but suddenly this number looks the same now, but the only thing that changed is that now it's 4.8 seconds per iteration instead of 4.8 iterations per second. This is due to this TensorFlow import, and somehow I have to figure out how we can change this, otherwise it takes so long, like 8 minutes for 75 games, or here 5 minutes for 75 games is just too long. You see Epoch 2, 124 files, the reward minus 38, minus 25. I'm not sure we can actually deduct that the bot is really getting better or if it's still some slight variation. 100 games is not that much. So yeah, here's already positive reward with 80% random moves. And then you see lots of errors, positive reward, minus reward again. Yeah, as I said, this is like not that many games, so we should run this for longer. It's terminated after Epoch 9. Yeah, I think this was just to see if it runs. I then took the model which went down to about 63% random moves. This is after Epoch 10. And then, 1 second, then I actually ran it with a couple of 0 epsilons to see how it behaves. And you can see all of those games have a minus 8. So we can look into the bot 0 log. This would be one example game. So it moved in one direction, having this as the Q values. And then it couldn't move, which is okay. Then it chose this move. And as you can see, it seems that our Q values here look all the same, which seems to me that we have some issue, like something seems to be buggy. It's also interesting that it actually always chooses the same move, so maybe this is correct and we just learned garbage. But I would be curious to now check some things. I think first off we're gonna commit what we have currently. So this is the change where we say we do not want to load TensorFlow if epsilon is 1. This is okay. This is where we want to store everything as states. Maybe I'm gonna undo this because we're just gonna unpickle whatever's inside. Then we don't see this. Yeah, maybe this one not. Here we have glob, tqdm, and numpy. This is okay. Starting epsilon should be 1. This is good. And we have this long loop. So we have our epsilons. I think we did all of this in the last episode. Yes, okay. This is episode 4, I think. Commit. Oh wait, let's just see. We so far we only committed episode 1. Interesting. Then this is probably the remainder of episode 2. Implement training. Okay. We'll check out. So we reverted this change. Git ignore. We do not want to have. We do not want to have replay. Block should be there. Replace. Does it work without log? Okay, I have to look at this another time. Okay, why could it be that we do only always predict the same queues? This is actually predicting the current state. So one thing I will do is I want to delete the model summary, and we leave the training data for now because I think it's not necessarily corrupted, especially the 1.0 training data. And then I will debug this by actually, okay, we import TensorFlow now in every game. We will run a random game, and we will logging info possible moves. We always log the current queue. So now we will do random moves 100% of the time. I also added this script, which will allow me to do this. Let's just add this here so we can decide how much randomness we want to have in our bots. And we will always print the model prediction. So I will just move this here. Again, this is just now duplicating it. So Instead of doing random and can't move, I always want to store what the model would have said, although I will only make a random moves. So first I need to run the training py again to actually create our model again. Model is created. So now we run the first game. You can see there's some debug output now from, yeah, okay. And I actually, this is some change I made in between for debugging purposes. Oh, do I still have this running? So I can just copy and paste this and run this. So I ran one game. And as you can see here, we have different predictions for the different states. Of course, if you do 0, 0, what would change in the feature so that we have a different prediction before? Of course, the input changes because we are collecting resources. So this is fine. Okay, this looks good. So apparently our network only learned crap during the time. Okay, so I think this is fine. Let's undo this. And then maybe we collect just a lot more random training data. So let's do epsilon decrease. Let's half epsilon. Let's decrease epsilon much faster. Let's half it in each episode. Let's run number of epochs, and then let's run 150 games. Or let's okay. Let me get another 1,000 games in. And here we can also run maybe more. Let's run 10 epochs in the neural network. Oh yeah, and one thing I said before is we are actually trying to model the DeepMind paper, right? And then I just copied the network that I had before. And let me just check if we keep this, or it doesn't matter that much. So if you're curious, I said we're gonna use some of the tutorials that you can find on Medium or Free Code Camp or whatnot. So here we have a tutorial by Thomas Simonini. Sorry for butchering your name. Simonini. Yeah. And as you can see here, also explains the difference between Q-learning and deep Q-learning. And then in the DeepMind paper, what they actually did is they have some Doom image, they grayscale it and normalize it to 84 by 84, and then they stack frames onto each other to get history and know where stuff is moving. And then they put convolution on top, first 20 by 20 by 32 patches, then they do batch normalization and ELUs, then a 9 by 9 and a 3 by 3 convolution with 32, 64, 128, then they flatten everything, fully connected, 512, and then the output units. We don't do strides in our current setup. Our stride is 1. We have a 3 by 3 kernel. Here they have a 8 by 8 kernel. We have 64 filters. So I feel I'm actually not sure why they use. Okay. On an 84 by 84 picture, maybe the stride is fine because you don't need to know what happens on a pixel by pixel basis. But in our case, we actually want to know what happens pixel by pixel basis. Our field is not very big; it's 8 by 8, and we care exactly where is resource and what's happening. Our kernel size is 3 by 3 because it's the smallest one. It makes sense. Here, 8 by 8 is just, again, I guess, you don't necessarily care about the exact pixel here. So this is very similar. They have only one fully connected layer with more dense neurons. I don't think we care too much about that. They have a ELU activation. We have a ReLU activation. I wonder if this is any difference, but I think not. Padding, I have same, they have valid. I think this also doesn't matter too much. Yeah, so I think we can just go with this network and not care too much. Let's run the training real quick. Yeah, I should have removed this print. This is a bit annoying. Where did I? Later on, we can also parallelize this. So I don't know, I can run more than one game at once, especially with these TensorFlow imports. You can see right now 3 games per second, something. This will still take 5 minutes or so. Maybe we can go a bit through this blog post. So one reason for grayscaling is just remove the dimensions. You don't care about the colors, you just care about the shapes and stuff. And you have some variability in the darkness and everything, so this is enough. And then they stack frames on top of each other so that you can model movement. If you just have a single picture, you don't know in which direction is this enemy moving, in which direction was I moving. This is one way of solving it. Then here it says there's a blog post where someone uses LSTMs to solve this, so the network can remember in which direction was something moving. Yeah. Now you will hear my laptop fan going up. I'm sorry for this. This will make the audio quality be a bit shitty, but we'll stop this soon. Then there's this avoid forgetting previous experiences. This is basically, they found if you do it similar to this gym environment where you take an action, you immediately get the state and the reward, and then you can do this for a couple of steps, and then you just train your network, and then you do it for a couple of steps. After you complete some of the levels and you will go on to the next level, the network will actually just forget how to beat the previous level because it doesn't see any samples of this anymore. And in order to avoid this, you just keep a huge array full of samples from all the stuff that you ever saw, and you randomly sample from that. So even if you're in Super Mario level 2 or 3, you still sometimes sample something from Super Mario level 1, and then give this to the network so that it doesn't forget that it ever saw this level. Like here, yeah. By learning how to play on the water level, our agent will forget how to behave in the first level. Stuff like this. Is the replay buffer, then correlation of experiences. I think this is also related to the replay buffer. And here's the formula again. If you want to check it out, this is our Q value, we have the learning rate, we have the reward, we have our Q value, and then this is actually already the update term, which is handled in the fit method for us. Then here's the implementation and the final thing. So I think technically the implementation as we have it should already be working. I assume though that since we only have 10 steps in each replay, we just need a couple more games, or train on them longer or something. Decrease the learning rate. There's so many like little knobs that you can crank and turn. Maybe this network is already too I want to say big and complex for the problem. Since we only have one level, it's always the same. It's just 8 by 8. Let's see. I think we can just stop this here. I hope this doesn't screw up the audio too much. Eventually I'm gonna get a proper microphone. Let's just run another 10 games and then train it for 10 epochs. Oops, invalid literal. Oh no, I know what we did. Oh no. I actually reverted the change that we want to store this one with an underscore as to avoid that's not good. How do I fix this? I could just throw everything away and just rerun it. It doesn't take that long. Maybe that's what we're gonna do. Oh, look, here's a 700, a sample with 700 reward. Another thing I wondered is the highest so far I've seen is 1,000 something. I wonder if it's impossible in 10 moves to crash 2 ships together, build new ships and crash them again. Probably. That's why we don't see any rewards that are lower than this. You might also say, oh, if let's immediately. This is annoying. Yes, yes. No, this is just for playing. Yes. Yeah, why not? Let's amend this to the last commit. Oh, what's happening here? And push this. I will probably like off video run this because it takes a while, and it's probably not so interesting to look at it, and then we'll just pick up right after. The next thing I think we would do is see if we get this model trained somehow. So if this model can learn to beat random every time on these 10 initial moves. That's what I would call a success, and then we will just turn up the complexity, like use more turns. As soon as we use more ships, we will probably use the same trick with the frames, stack them on top, and that is it. I hope it will learn to properly move ships around and collect resource then. The next complexity we would want to add is like how do we incorporate information about the rest of the game. As you can see here from the nice drawing, we have he has some opponent features, some meta and map features, and we would have to incorporate all of this in order to let our network also decide whether it wants to build ships or move, how it wants to move the ships. So this was an episode that was mostly talking. But I will run this now and see if we can get this learned. See you.